Hi there, welcome back to the channel for another Verilog project. In this video, we'll be discussing about Round Robin Arbiter or scheduler circuit and its implementation using Verilog HDL. The code is implemented on EDA Playground, which is a free web simulator that allows users to edit, simulate, synthesize, and share their codes easily. Let's first look what an arbiter is. So in computer systems, we have multitudes of resources. In simple language, a resource can be a computer program, data, storage devices, communicating devices, or maybe networks. So usually a particular resource is used by only one device at a time. But do you know what happens when we have various devices that needs to use that resource? Correct. These devices have to request for it. And rightly guessed, these requests are handled by an arbiter circuit. Therefore, an arbiter is a logical element serving to select the order of access to a shared resource. As can be seen over here, we have four requests: request 1, 2, 3, and 4, which are being handled by an arbiter circuit, which is further followed by a shared resource. So, an arbiter would select the appropriate requests, these four requests, as shown, that would use the particular shared resource depending upon the algorithm that the arbiter would use. Henceforth, scheduling algorithms or arbiter are used when multiple requesters require access to a shared resource. So let's take in two examples to understand where scheduling is used. First, SoC or system on chip, that is, integrated circuit that holds many components of a computer. And these components could be a CPU, that is, microprocessor or a controller, memory, IO ports, and secondary storages. These all are placed on a single substrate. So we know that we have multiple devices and these may require CPU execution at various instances. Therefore, a powerful arbiter becomes important to serve all these requests. Another example is of network switches. So we know that in network switches, we have various data to transfer in the form of packets. So here as well, a scheduler is used to maximize the throughput. That can be done by minimizing the wait time for each request in the form of data packets. Now that we have understood what an arbiter is and its uses, let's delve to its one of the form, the round robin scheduler. The round robin scheduler, in its basic form, is a simple time slice scheduling that allows each process requester a share of time in accessing a process in a circular order, that is, fixed time slot per requester. As you can see over here, a circular queue is illustrated that has 6 processes P1, P2, P3, so on till P6. And each process is provided time slices or time quantum in equal proportions and in a circular order. So all these process segments are executed in equal time frame. That is, their access is based on TDMA, which implies time division multiple access. So first CPU scheduler executes P1 for a fixed time slot, then it transfers over the execution to P2. Then P2 execution happens, then it would further give it to P3, then again to P4, P5, P6 in a consecutive or a round robin fashion. The most important feature being it is starvation free, which implies that no process is denied necessary resources to process its work. That means each process would get its portion for CPU execution and hence won't starve out. So let's take in one example to understand the concept better. Take a random process that takes in 250 milliseconds to complete, which implies the burst time is 250 milliseconds. Let the time slice or the time quantum for each process be 100 milliseconds. This means the process would require 3 quantum CPU allocation to complete its execution. So first allocation happens for 100 milliseconds for process P1. Then subsequent processes that is in circular queue happen in round robin fashion, that is P2, P3, P4, P5 and P6. Again, the second allocation would happen for another time slot of 100 milliseconds. And during the next allocation, the forced termination would happen after 50 milliseconds. So why waste the leftover time slot if your process is complete? So as you could see, the time slot was of 100 millisecond, but the process execution forced terminated after 50 millisecond itself. So now coming to the rotary bus access. So in a shared bus, the arbiter determines which master uses the bus. So here, each master requests for the CPU access for the process execution. And when a master relinquishes the bus, the switch is turned to the next position and the bus is granted to the master on that level. So by relinquishing, I mean is that the process gets completed and the switch or the CPU access goes to the next process in the queue. So as it can be seen, we have four masters over here: 0, 1, 2, and 3. And currently the bus access is with master 0 and the corresponding process is being carried out. The next switching position is with master 1, to which the black arrow is being pointed to. Further, requests move on to master 2, then master 3, and again to master 0 if process isn't completed. And this process reiterates. Now coming to the scheduling flowchart. Initially, we have a ready queue wherein all the processes P1, P2, so on till Pn are laid in a round robin fashion. The bus access is then provided to a specific process for initiation. Then we check if the burst time, that is, the time required for process completion, is greater than the time quantum, as was the case in our example where we had the burst time as 250 milliseconds and time slot as 100 milliseconds. So if it's greater, then you execute for that particular time quantum, then wait for that time quantum to expire. You check if the process execution completely, then you would terminate, elsewise you would reiterate the process and then wait till the burst time is less than the time quantum. When the burst time gets less than the time quantum, you would execute and then force terminate as and when the process gets completed. Let's now delve into the arbiter general topology, wherein we would look at the circuit first and then move on to the Verilog code. So here we have various blocks. We have the arbitration logic block, we have the encoder logic block, then you have the storage register block, you have a communication signal block, then you have the state machine and multiple signals in here. So in the forthcoming slides, we'll take a look at all these blocks and their functionality with the Verilog HDL code. Moreover, before starting, I would like to mention that the code has been written taking into account 4 masters, although the number of masters can be increased as per the needs and requirements following the same procedure. Let's start with the first logic block, the arbiter logic. So herein we have 4 inputs and we have the 4 outputs with the presence of a clock signal. So from the 4 masters that we are taking, the bus request would appear at the input ports request 0 to request 3. If the bus access is free for CPU execution, one of the 4 grant lines, grant 0 to grant 3, is asserted, describing to which the request does it corresponds to. Further, these signals would be encoded via 4x2 encoder, as we'll see further in the upcoming slides. And moreover, the block is synchronized with the input clock. The sample clock pulse will be implemented in the test bench, as we'll see further. The second is the communication request logic block. So the following block is a multi-input single output kind of a block, wherein we have 4 request signals, request 0 to request 3, followed by an output signal as communication request. That indicates whether the bus is free or busy. So it becomes active whenever a master has both requested the bus and has been granted the bus at that moment. And logic 0 would represent that the bus is free, whereas the logic 1 represents it is busy at that particular moment. The third is the encoder logic block. So the 4x2 encoder circuitry would take in the 4 grant signals, grant 0 to grant 3, generated by the arbitration logic block, and further generate a 2-bit encoded signals. So using the encoder, we know that it reduces the hardware complexity of the circuit due to the reduced number of connecting wires. So it is moreover used with communication request signal to indicate which master has been granted the bus. So when communication request is active, that is active low, that is the bus is free to use. So the master located on grant 1 to 0, that is the encoded grants, is granted the bus. Let's now see the encoder logic circuit and its truth table. So on the left, we have the encoded logic circuit diagram, and on the right, we have a truth table. So we have four grants as the input signals and then the two encoded signals. When we have the grant 0 as active high, that means we have the first request, then the encoded signals become 0 and 0. When we have a request at grant 1, then it becomes 0 1. For grant 2, it becomes 1 0. And similarly, for grant 3, it is 1 1. And the following circuit diagram can also be drawn with this truth table. So we can see like grant 1 is a combination of grant 2 and grant 3. That means when you add the grant 3 and grant 2, you get the encoded grant signals. So we have 0 0 0 0 0 1 1 0 and the output being 0 0 1 1. That means the encoded grant is equal to the input grant 2 or grant 3. Similarly, grant 3 grant 0 is equal to grant 3 or grant 1, and the circuit can be drawn as follows. So before explaining the state diagram, we see the begin input logic. So this input logic is the scheduling initiator circuit. Only when it is active, the scheduling process would happen. So the inputs are requests of the masters and the communication request signals, which are connected as follows. So let's see, just a second. So if we have any of the requests as high, active high, and we have the communication request as 0, that means the bus is free at the moment. So here we would get a active high signal. This would be 1. So this OR gate would be active high whenever a request is present at the encoded logic. So when both of them are 1, the begin signal would be 1, and we could then start the scheduling process. So this is really important logic to start off the scheduling circuit. And we could see like begin is equal to request 0 or request 1 or request 2 or request 3 and the negation of the communication request signal. Next is the register block, which keeps track of the level of the previous master, that is the previous request. So the level is saved in a register that latches the state of grant signal, that is the encoded output grant 1 and grant 0. The register latches the grant signal when is indicated by the state machine, and the count enable over here is activated with the help of state machine logic block. Now let's define the state diagram for a data flow model. We have inputs, we have signal states. The input is represented by a begin signal. As we saw, that was our scheduling initiator circuit. And the signal states are the encoded grant values, the output value of 4x2 encoded signal. So when the signal state is 0 0, request 0 is active and it requires a CPU execution. But if begin signal is 0, you stay on the same state. And if the begin signal is 1, that means you have the signal to start off the scheduling process, you execute the process and give the bus access to request 2. On the same ground, you check for begin again and then move ahead to the various requests in a round robin fashion. Request 1, 2, 3 and 4. For the fourth request, I have a don't care because either it begin signal is 0 or 1. On both the cases, you move back to the request 0. So this was our state diagram, and further we'll be looking at the Verilog code for this process. To understand the code better, let's first see the timing waveform that we got by simulating the code for 4 request signals. There's a reset signal RST. When active high, no scheduling happens. It's just like the begin signal we saw in the general circuit topology. Therefore, in this region, no scheduling process would happen. We have 4 request signals and their grant signals over here. Here, one time slot is equal to 10 milliseconds. For process P1, the burst time is taken to be 20 milliseconds. Therefore, it would require 2 time slots to complete the process because one time slot is 10 milliseconds. For process P2, P3, P4, burst time is less than equal to the one time slot and hence gets completed in one clock cycle itself. Therefore, during the positive clock pulse, the process P1 requests for the bus access, and in the next positive clock pulse, a grant is given to it. Similarly, for other processes like P2, P3 and P4, you give the request and in the next clock pulse you get the grant. Similarly for P3 and P4. But P1 will take 2 time slots to complete. It still remains active high even when process P2, P3 and P4 are executing because it's a round robin fashion. Therefore, they happen in a sequential way. So process P1 happens, then P2, P3 and P4. But P1 is still active high. And when all the processes are executed once, therefore in the next cycle, process P1 would execute again to complete its execution. Now that we have seen the timing waveform, let's look at how the grant values are given in the arbiter data flow modeling using the non-blocking statements. So here we have the request signals, the latch mask register values, which store the register block values. So these represents the 2-bit encoded grants, the output of the 4x2 encoder, which gets stored finally in the register value. Then we have the communication request signal. So for all the grants, various cases are taken out here for complete modeling. Since communication request states whether bus access is available or not, firstly we'll check that, then the mask register values, and then followed by the request signals. So for example, if communication request is equal to 0, this means the bus is free to use, and the last mask 1 and last mask 0 values are 0, 0. Therefore, stored grant values are 0, 0. Therefore, request 0 has to be catered first. And if the request 0 signal is 1, with all the other requests, request 1, 2 and 3 being 0, then we get the last grant value as 1, whereas last grant value 1, 2 and 3 are 0. Therefore, this request would be granted the bus access. So here we have the various cases out here. Then we can look for other cases as well. So let's check this example. So when the CPU access is with master 1, which is represented by mask register values as 0, 1. So LMask 1 and LMask 0 would be 0, 1 respectively. And we only care about the request 2 and request 3 signals. In the next case, currently the bus access is with master 2, where last mask value is 1, 0. So here it would be 1 and 0. And request 3 and request 0 are to be considered next for the grant 0. Similarly, the final case, when we have the master access to third case, then we have the LMask 1 and LMask 0 as 1, 1, and we only check for request 0. So here we saw all the cases for the first grant. These could be implemented to various grants uh, for for grant 1, for grant 2 and for grant 3 as well. Let's simulate the code and test bench in EDA Playground now. On the left, we have the test bench, and on the right, we have the Verilog description. The description starts with the module declaration with the name Arbiter with various ports like clock, reset, request, and grant signals. We declare the ports as either input or output ports. Then we have various internal registers as grant, communication request, begin, and then we have multiple latch signals. So we have used latch values so as to store the values for few clock pulses, and then finally we transfer these values to the wire variables. Let's now come to the always block, which works during every positive edge clock. So inside it, if reset is true, then all the grant values are reset to 0 value. Elsewise, we run this code just as we saw in the presentation, where we have multiple grant values and their various cases depending upon what request signal we have, what mask value we have, and what is the value of the communication request signal. We have the begin signal, which describes whether the scheduling process should happen or not, which with the given value as follows. Then we have the communication logic, which gives the bus status with the value as follows, and the encoded logic block, as we have the grant value L grant 1 latch grant value 1, which is given by grant 3 or grant 2, and the latch grant 0 as the latch grant 3 or latch grant 1. Then we have the mask register, which again works during the positive edge of the clock only. If the reset is high, you give the mask register values as 0, 0. Elsewise, we check for the mask enable. So mask enable is an enable for mask register it gets enabled when there's active high signal from the state machine block. So when it's active high, you give the actual values of the grants to the mask values. So if the, let's suppose the encoded grant values are 0, 1, it would store 0 and 1 in the mask register. So it would save that particular grant value in that register. If not, if mask enable is 0, you stay with the current value itself. And in the end, the latch grant values and the latch communication request value are stored in a separate wire variable. And we give all these grants and store it in the wire grant variables using the assign statements. So this was the Verilog description. And now coming to the test bench. So herein we define a module with the name of top. We have various signals defined via register and wire as clock, reset, request and grants. Then we define the clock generator as follows. We have one initial block with these statements. So we have a dump file and dump var statement wherein we dump the changes for all the variables in the file to draw the waveform. Then I've taken a specific case where to understand the working of round robin algorithm. So it's a sample case. You could also make changes to it to understand it better. And in the end, I have connected the design and the test by instantiating the module arbiter over here in the test bench. So now let's run it. So here is the timing waveform, just like we saw in the presentation. So we have reset, request and grant signals for that particular case that I have taken in the test bench. So you could try for various cases by changing the this part of the code. So you could change this part of the block and try various cases to understand it better. So by this, we come to an end of the Round Robin Arbiter tutorial. And if you like the video, do consider liking, sharing the video and also subscribing to the channel. Thank you.